I'm really glad to give this lecture. It is going to be on data-driven models of human behavior. It's going to be 3 hours. I would suggest that we make a break in the middle. It's easier for you and it's easier for me. So after more or less 1.5 hours, we can make a quarter-hour break if you agree. Okay? I'm from ENS Lyon and I'm also have a chair at INRIA. I'm actually, as Alan explained, working at ICSI, sitting at ICSI. I'm sitting at ICSI, which is the Complex System Institute in Lyon. Today, I would like to talk about topics grouped in around three different phenomena. I would like to talk about human behavior on the individual level, then human behavior on the group level, and finally about human behavior on the collective level. So this is actually what I'm going to talk about today is based on my course on modeling social systems, which is way longer than the 3 hours today, so I have to skip a lot. I hope it still remains comprehensive over the course of the lecture. Some technical details, you can find here the slides in a PDF format. There is a login and a password. You need to remember to log in to download the slides. I can probably write there on the table, blackboard in the break if you would like, if you cannot remember these numbers. Okay? In terms of literature, I'm going to give you several slides on the literature during the whole course. The first one is this one. This is actually covering a general view on computational social science, and also there is this very nice review by Castellano, Fortunato, and Loreto on statistical physics of social dynamics. This is not a very new review. It was published in 2009, but it is actually containing all the basic models and concepts which has been introduced in the last 50 years in order to understand quantitatively and model social behavior. Then there is this other paper. It is a seminal paper founding the field of computational social science with many distinguished authors. You can also read this if you're interested in the subject. And these are actually more topical papers on different questions we are going to address in the first part of the lecture. The other thing is that I may talk too fast. I may talk not loud enough. Plus, I don't like my voice so much. So if you would like to talk or ask questions, make comments, please just interrupt me. Okay? So I would like that it's more like an interactive course rather than I'm telling you something and you have to believe in it. Okay? In order to motivate my lecture, first I would like to talk about computational social science in general. I know that last time you have had already a speaker, Camille Roth, who talked about computational social science. I hope I will put it in a not very different, but yet a little bit different perspective. So why computational social science is important is because of this. So it has been a large attention lately, not only from science, but also from policymakers and from industry, in order to understand human behavior in a quantitative way. Of course, this is not happening just by chance. It is happening because we are entering an era where human behavior is observable way better or way easier than it was done before. The best example is actually just by looking at how many, what kind of things and how many of them are happening on online social networks, on online social systems. This is actually a website where you can go and it will show you that in every second how many tweets has been posted and how many wall posts has been posted on Facebook and so on and so forth. As you see, this is an incredible amount of data. All these data sets are somehow recording human behavior, which means that by analyzing this data, we now have a chance to make quantitative observation of human behavior, to identify motives and correlations, how people act, how people interact, how people move in space. And this is actually which is giving us the chance that we can establish the field of computational social science. Also, these different platforms give us a chance to address or observe people in different aspects. So, for example, to see what kind of different behavior they can post on that. So this is a very nice diagram about what can you tell about your cat online. For example, on Facebook, you can write that I like my cat, Or on Twitter, people used to say, I'm playing with my cat. My favorite is Google+. I'm working for Google and I have a cat. Why? Because no one else is posting anything on Google+, just the Google employees, right? So by observing people at the different platforms, you may understand different aspects of their behavior. Whether they are talking about something, whether they are advertising something, whether they are commenting on something, and so on and so forth. So different data sets are helping you to understand human behavior from different angles. Next question is that what is the subject of computational social science? Computational social science is, in my understanding, addresses 3 levels of human behavior. First of all, it is trying to understand the dynamics of individuals as an individual and also as egos in their socially embedded environment. For example, one can look for how individual actions are evolving as a function of time. We are going to do this in the beginning of the lecture, first part of the lecture. Then you can also understand how an individual is interacting with its egocentric network, its immediate social environment, and for example, how it is moving in space to understand mobility patterns. A second subject of computational social science is on the mesoscopic level to understand how people interact with each other. So how they form groups, how they form communities, how these communities are connected together, how they form, what are the mechanisms which form actually their egocentric network and the connectedness of the egocentric network. While the third level is the collective level, maybe the one that people used to think the most about. In this category, one can address phenomena about social contagion or collective motions, like for example, crowd movements or flocking of animals even are belonging to this category, or opinion dynamics, or for example, how riots or revolutions are emerging in society. Next question, now we know that what we can learn with computational social science. The next question, how we can learn this. And of course, as I already mentioned, the main advantage of computational social science is that we can make data-driven observations on large digital collected data sets describing the behavior of millions of people. So here we can first apply data mining techniques in order to infer some correlations of human behavior, describing, for example, how they interact with each other. Then using these mechanisms, what we identify from the data, we can go to our model, typically agent-based model, where we try to integrate this mechanism and try to reproduce what we have observed in the social system, in the data. And once we are done with this, we go back to our data and see whether we succeeded or not. Usually not. Okay? So this is the typical cycle, research cycle in computational social science. Of course, once you failed to verify your modeled system, you can start all over again. Very well. And the last question I would like to answer to motivate my lecture is, why is it important? There are actually 2 whys, or 2 answers to this question. The first answer is more a general scientific answer. Why we are dealing with computational social science? Because actually it has a chance to somehow introduce social science as a quantitative field. It has been a qualitative, theory-driven, hypothesis-driven field earlier, based on small-scale experiments, observations on census data, but all of these approaches had their advantages and disadvantages. On the other hand, now we have a chance that we can make unbiased population scale, individual level observations of millions of people. So actually we can quantify observations. We can put numbers on things, we can calculate precise correlations without even very, very advanced statistical techniques on 10 data points. Now we have millions of data points. So we have a way better chance in order to, I don't say that we are trying to push this field towards to become a deterministic field like physics, because society is not a deterministic thing, but we may have a chance to identify correlations or patterns, what we can use later for understanding them. There is another pragmatic answer, more pragmatic answer of the why, it's because of prediction. So what we are trying to do, we are trying to predict social ties how different products are adopted. We are trying to predict what will be the outcome of the next French election, presidential election. We would like to predict popularity context at epidemic outbreaks, and so on and so forth. Even we can try to predict wars and emergence of wars and revolutions if one has access to data like this. Think about the Arabic Spring, for example, which is now studied after its emergence in order to see whether on social websites, what are the signs that something is going to happen next. So that's all about computational social science. I just wanted to put my lecture in a context that you see from where we are starting and where we are heading to. As I told in the beginning, we are going to discuss 3 levels of human behavior. The first one is the individual level, and we are going to talk about bursty human dynamics here. Do you know what is bursty human dynamics? Guys who know me on the first name base, don't answer. So, any idea? What could be bursty human dynamics? So, the original idea or the original assumption about human behavior was that we are all Poissonian agents. What does it mean? It means that if I'm observing a person, let's say I observe myself, and I'm just I'm identifying the time points when I'm sending an email. I send an email at 10 o'clock this morning, then at 10 past 10 this morning, and so on and so forth. Each time I send an email, I can draw a line, I can identify the time when I send the given email, and I can draw the timeline of my emailing pattern, assigning here a black line the time when I send an email, and the white period when I do nothing. The original assumption, which was like until 20 years ago, was that when we think about the dynamics, for example, email sending of people, we behave as such as a Poissonian agent, which means that whatever we do, it comes with an approximately constant rate as a function of time. This can be actually described more quantitatively by measuring the inter-event times. Inter-event time is defined as the time between 2 consecutive events, the time between I send 2 consecutive events. Okay? If I assume that I am a Poissonian agent, it means that I have a characteristic time scales. On average, every 10 minutes I send an email. Okay? Of course, there are fluctuations. There is a process, as I explained already, as I mentioned already, which describes this type of dynamics, the Poisson process, which actually determines that the number of emails I send within a given period of time is distributed as a Poisson distribution. From this, it's easy to derive actually that if my action rate is coming as a Poisson distribution, the time between consecutive actions is going to be an exponential. Okay? So inter-event times, in case of a Poisson process, are distributed as an exponential distribution. Is that clear? Why is it wrong? It is actually wrong because we are not Poissonian agent. The Poisson process assumes that whatever we do is independent of what we have done before. It is assuming that my next action is not depending on what I have done even right before or in the last 10 hours. Okay? It is assuming that all of my actions are independent and coming with a rate can be characterized by a Poisson distribution. Okay? So if you assume this, our signal would look like this, right? So we have a more or less constant rate of actions. This is actually a plot which is assigned the inter-event time distribution between consecutive events. You see that there are no large deviation from the average. More or less all the inter-event times have the same value. If you look at the distribution of these times, so inter-event times here on the y-axis, you arrive to an exponential distribution by definition because this is a Poisson process. The only problem that when you look at real human behavior, it doesn't look like this at all, but it looks something like this. In case of human behavior, you don't have a constant rate of action, but you have periods where you do a lot of things, you send a lot of emails, and there are periods when you do nothing. You do something else, more precisely. Okay? So it means that you cannot be characterized as an individual. Your actions cannot be characterized as a Poisson process because it is something different. If you look at the inter-event time distribution, you see that actually there are very, very large inter-event times assigning these long periods when you do nothing. And there are short inter-event times assigning those consecutive actions which happens in a burst. And this is now, we arrive to the naming why it is called burst. Because you have this period when there are a lot of things happening. This is what's called burst. It's coming from, I think, solar flakes, and also in case of package transmission in computer networks, they also use this term, and in neurology as well. Okay? In case of humans, it was actually defined, we can say that it was, I don't know whether I'm true, maybe people will kill me, but the first time I heard burst in terms of human behavior, it was the Borobashi book, which was in 2007, something like this. Okay? So in case of humans, it was this naming was actually borrowed from other fields where similar phenomena has been already observed. So how can we characterize this? How different this from this is very easy. If you look at the inter-event time distribution, actually it is not an exponential, but it's going to be a power law or something similar. Assigning that there are large heterogeneities in inter-event times, there are long inter-event times rarely occurring, while most of the inter-event times have a very, very small value. There are a lot of actions which are happening within a short period, and then there are long periods when nothing is happening. Okay? So once you have this picture and you go to your data set and you try to observe human behavior in different aspects, you find that this is actually true in many different cases. First of all, it is true not only in case of human behavior, but in other natural systems, like for example, case of earthquakes. It is sequence of earthquakes in a given Japanese city, or this is the firing of neurons. They also show similar patterns. But you also find burstiness in human dynamics. This is, for example, mobile communication. These are inter-event time distributions of the mail, like post-mailing of Freud, Einstein, and Freud, Einstein, and Darwin. Sorry. But also, if you look at how people are browsing on the web, for example, time between consecutive clicking or visiting a given website, or how they send emails, how they go to the library, and so on and so forth, they all can be characterized by broad power law. Let's remain with the word broad inter-event time distribution, assigning that all these systems are burst. Okay? Why I am hesitating to call it as a power law? Because actually the main claim is that this is a broad distribution, but can be fitted with many other different candidate functions, could be maybe fitted by a power law, or a power law with an exponential cutoff, with a log normal, with a stretch exponential, and so on. What is important is that when you look at the probability density function of inter-event times, you see that they are ranging over several orders of magnitude, assigning large heterogeneities in the dynamics. This is, for example, a good, medical horse of inter-event time distributions. This is inter-event time distributions of mobile phone calls. Here you see a peak. This peak is at 20 seconds. This 20 seconds is typically the time what people use to answer a call. Okay, so that's why this peak is here. Then you see another peak, which is at 24 hours, assigning our natural, the circadian pattern, also assigning that our actions within 2 days are less correlated than within 1 day. Okay? On the other hand, you can also ask the question that, good, I see that there are bursts of human behavior, there are people used to behave as a function of time in a bursty fashion, but we are different in many other sense. For example, if I look at my emailing pattern, I send about 10 times more emails per day than my wife does. Okay? So there might be other differences between people, for example, in terms of their activity. If you, on the other hand, if you look at people and decouple, group people by their activity, so first group people who send only 10 emails or make 10 calls, then other group who sends between 10 and 20, 20 and 40, and so on and so forth. And you look at the inter-event time distribution of these different activity groups, you still find a bursty pattern. Moreover, you can actually scaled by the average of the interim and time distribution, all these interim and time distributions on a master curve, assigning that burstiness is more a universal human behavior, independent how active I am. Even if I'm sending 10 emails per day, I do it in a bursty fashion, the same way if I would send 100 emails per day. Okay? Also, you can see that this is an equivalent distribution of the same number of events, just after a shuffling method, Poissonizing the given dynamics. You can see that this is an exponential distribution actually. What we observe in reality is rather different than what we would expect from a Poisson process. So there is something intrinsically different here than the original assumption was that people are Poissonian agents. Okay? Very well. So after this observation, the next question is why? There have been several proposed models in order to describe bursty phenomena, bursty human dynamics. I'm going to walk you through two concepts, two competing concepts actually, which are actually using very different assumptions in order to explain this dynamics. The first one assumes that whatever we do is driven by our circadian pattern. What does it mean? It means that during the night we sleep, during the day we don't. So I don't send emails during the night because I'm sleeping. So naturally there has to be long interim and time distributions because during the night nothing is happening. And there are short interim and time distributions because during the day I'm sending emails. Okay? You can also observe different patterns by looking at the circadian fluctuation. This is actually lunchtime when people go out for lunch day. This is mobile phone call activities for different days as a function of time. During lunchtime people call, they go back to work, they are out of work, they go to sleep. Okay? So just by this, the question whether we can still assume that our actions are independent, but just by the circadian pattern, it is regulated as such that as a consequence, we observe a bursty pattern. So this is one possible reason. Another possible reason could be that actually our actions are not independent at all. What I am doing is depending on what I have done before. So one sign of it is actually this 20 seconds at the peak of the interim time distribution that I just mentioned, which is assigning that there is some causal relationship between consecutive actions. I'm calling back someone because someone called me. Okay, so the incoming call is causing me an action to make another call, which means that these two actions are not independent from each other, but there is a causal correlation between them. Okay? You can also observe signs of this type of phenomena by looking at the call sequence of a given person. These are the time when this person called someone, or this person was called by someone. And then you can decouple this sequence to he had or she has 3 social ties. This is when he or she was communicating on social tie 1, on social tie 2, and social tie 3. Okay? And then you can actually observe periods. This is just a zoom in, where you see that there are simultaneous active periods on different social ties, assigning that this is a kind of a group communication, that I'm talking to one friend and then at the same time I'm talking to another friend, maybe because I want to have a beer. Okay? So from data you could observe that there might be some signs of correlations between consecutive actions of people. We are not Poissonian in that sense. Okay? So, taking the first assumption, the first paradigm in model in bursty human dynamics assumes that we are actually Poisson agents. There is this seminal paper by IMéRA and Malmgren in 2008, where they very well formulate these two paradigms what we are going to talk about. One hypothesis says that human behavior is primarily driven by rational decision making, which introduce correlation in activity, thereby giving rise to habit tails. So this is one reason that we have bursty behavior. And the other is human behavior is primarily driven by external factors such as circadian and weekly cycles, which introduces a set of distinct characteristic timescales, thereby giving rise to habit tails. So the first one assumes that we are conscious correlated entities. The second assumes whatever we do, it is due to the circadian pattern. Our actions are independent from each other. Just due to circadian pattern and weekly cycles, we can reproduce the burst observation. Okay? So, actually in this paper, they were taking the second assumption, and as I will show you, they made a very charming model of bursty dynamics. Their assumption was that periodic patterns and uncorrelated actions are enough to explain temporal heterogeneities. Okay. The model is very, very simple. It takes an email try to model an email corresponding of a person, which typically looks like Marton goes to the university, checks his emails, and responds before the classes. Okay? Then Marton is not checking his emails until lunchtime, ideally. At lunchtime, he is sending 2 emails. Then he checks his emails before sleeping and during the night. And during the night, he sleeps, he doesn't check his emails. And he's out for the weekend, and he's not checking emails for the whole weekend period, so they will belong in the okay? So it means that my daily pattern, because I have other things to do and I have to sleep, is completely determine my actions. Actually, my actions, my emailing, is coming in short periods, what's called active periods. When I go on my Gmail, check my mails, answer 3 emails, then I do something else. So their assumption is that the email pattern of a given person can be simply built up by the convolution of these different type of time scales and active periods. So one time scale is characterizing our weekly pattern, which is during the weekend we are less active, during the weekdays we are more active. I think you can accept this. The second time scale describing our daily pattern, saying that during the day time we are active, during the night we are not active. If you take a convolution of the two, you will receive an activity periods where during the weekends, during the days, we are less active than during daytimes, during the week, and during the night we are always inactive. So their assumption was that, okay, now we identified by combining these 2 time scales overall activity signal. In each period when we are active, we can actually initiate an email session where I'm going to check my emails and I answer 3 of them at the time. Okay? Which means that these activity patterns are driven, the initiation of these active periods when I'm checking my emails is driven by my daily and weekly pattern. Okay? So their model is very simple. They are distinguishing between active and inactive periods. In an active period, which corresponds, for example, to this high peak period, the person can initiate an event avalanche, open Gmail, answer 3 or 4 or 5 emails, and then go on. Okay, so the model is very simple. It is built up from different Poisson processes. There is one Poisson process which describes this periodic fluctuation of different timescales. It's a non-homogeneous Poisson process, which means that the inter-event time distribution is coming as an exponential distribution where the parameter of the exponential distribution is time dependent. It is a periodic function describing our daily and weekly pattern. Okay? And the second exponential distribution, there is a second Poisson process, homogeneous Poisson process, which describes our inter-event time distribution once we enter an active, an excited, an avalanche period. Okay? In this second Poisson process, our inter-event time distribution comes with a way shorter, way smaller parameter of the exponential distribution, which means that our inter-event time distribution within an avalanche will be shorter, and between avalanches will be longer, determined by the non-homogeneous Poisson process. Okay? So actually what they can do, they can multiply it all together, which will tell you what is the number of events you are going to initiate, what is the number of emails you are going to send in a given period, from which you can actually extract the bursty dynamical pattern of interactions. Okay? The model is very simple. They generate an inter-event times between active periods using a non-homogeneous Poisson process. So these are the inter-event times between peaks over here. Then after entering an active period, sample a distribution to get the number of events in the actual avalanche. This will actually, once I'm inside a period like this, I'm going to decide how many actions I'm going to make, and then generate an interval times between events of the avalanche by a homogeneous process using another lambda parameter for the inter-event time distribution, which is actually way larger than the one describing my non-homogeneous behavior. Okay? So, as a parameter, what they have actually is the two Poisson process parameter. They need the number of events you are actually executing within one active period, the number of emails you send once you open your Gmail, and the lambda A parameter for the short inter-event time distributions within active periods. Okay, so the only thing what they have to do is that they go to the data. Yeah.
When do the avalanche end?
Yeah, it's very simple. Can I use that blackboard?
Yeah.
So how it goes is that, let's say that this was your last action. The first inter-event time distribution, the non-homogeneous inter-event time distribution, determines when will be your next active period. Okay, let's say it is going to start here. Once you are here, you are going to decide how many events you are going to initiate, how many events you are going to make. This is the P and A distribution. Let's say it is 3. So you know that there will be 3 events within this period. And the inter-event time distribution between these 3 events is coming from the other Poisson process, which has a very larger parameter, so shorter inter-event time. So it will tell us that the first event is here, the second event is here, and the third event is here. Once the events are away, you again sample a long inter-event time distribution from the non-homogeneous process. Yes, once it is done, this is one burst period, then you get another long inter-event time. Okay. So all you have to do is to go to your data. In their case, they went to an email data set of about 400 university students or accounts over 83 days. And they tried to fit their parameters on individual action dynamics. They looked at what time different people looked at a single person, look when this person was sending email as a function of time, and try to determine these parameters directly from the signal. So it was actually not very difficult. The lambda t can directly measure. The P and A, which is the distribution of emails in one active period, can be identified by simulated annealing, and the lambda A parameter could be calculated for the actual avalanche, what they were looking for. So what they found is this. Here, these are inter-event time distributions of different people, where the black line is the data and the red line is the model. Which is like, wow, okay? You see that the model could, with very large precision, reproduce what they have observed in the data. So it is actually a very nice presentation that, by this assumption that we are Poissonian and driven by the circadian pattern and the weekly patterns, we can actually reproduce what we have done. So there is no need to consider correlations between events in order to explain bursty phenomena. Where is the problem?
Maybe you could reproduce quite anything. So
exactly. This is the problem. With a set of exponential functions, you can fit whatever you want. Right? Because you can put together exponential distributions with a set of characteristic scales as such that it can become Poisson distribution, it can become exponential distribution, it can become power law distribution, it can become a Gaussian distribution, whatever. It is actually depending on the distribution of the parameters, which means that they are not explaining much with this. They are giving one possible way to reproduce the data. Okay? So for phenomenological modeling, it's very nice. For understanding it is not giving us the page. Okay? So there is another paradigm I would like to mention, which is based on priority queues. And using exactly the other assumption, namely that our actions are not independent from each other. Here, I think the best way to present the idea of this paradigm is with this PhD comics, which describes also my typical way of action. So first of all, I have a lot of things to do. So step one, I make a list of all the things I have to do, and then I assign a priority, which is the most important thing for the moment and which is the less important thing. Then I realize that there are too many things and too many priorities, so I first wash the dishes. Usually I don't wash the dishes, I do something else. Or I rearrange the icons on my computer, and then I freak out. All in all, what I would like to give as an example is that we can consider the things what we have to do always as a list of things where we have priorities assigned to the different tasks. There is always the most important thing, the second most important thing, the third most important thing. Sometimes the most important thing is to go to sleep. Sometimes the most important thing is to finish my thesis. Typically, we are working towards deadlines. These deadlines are all over and over reshuffling or resetting our priorities, because as we are approaching the paper deadline, we start to work more and more on the paper. Okay? So, all in all, the phenomenon or the assumption is that all the things that we have to do, they are not randomly selected, but they are assigned to priorities are assigned to them, which determines their importance, actually which determines what will be the next thing that I'm going to do. Okay? So, how can we model this? So let's assume that we have a number of tasks to do: eating, sleeping, emailing, calling, prepare slides for the lecture, and so on and so forth. And each of them has a priority. This priority determines the actual importance of that given task. Okay? And the question now is that how much time a task spends in my priority list before I do it. For example, if there is a task answering an email to my mom, how much time after my mom will send this mail, what I'm trying to answer to, how much time this task spent in my to-do list before I answer to my mom. Okay? There is a slight difference between this quantity and the quantity we so far talked about. So far we talked about interevent times, if you remember. Time between two consecutive actions. Here I'm interested in the time what the task is spending in my priority list. You can say that these are two different things. Actually, it has been mathematically shown that they are equivalent. So whatever I say about waiting times will be true about interevent times as well. Okay? Very well. So, next, I have this list of things. Each of them has a priority. Each task has a priority. I can select these tasks from my list in different ways. The first way is what's called Fifo, first in, first out. So if I have a new task coming to my list, it has to wait until all the tasks which arrived earlier before it gets executed. Which means that I'm always executing the task which is on the top of my list, which arrived earliest in time. Okay? This is one protocol I can choose in order to execute my tasks. Another strategy could be random strategy, which means that we are like monkeys, we are selecting randomly tasks from our priority list, don't care about priorities, saying that, okay, I have 5 things to do, let's do this first. Okay, my daughter is typically doing things like this, especially when it turns, we are getting close to bed. Okay? And the third is a priority-based strategy, and this is more like how humans are behaving, is that you have a list, each item is assigned with a priority, items are sorted based on their priority in the list, and you execute always the one which is the most important at that time. Okay? So next, let's define a very simple model. Assume that we have an individual with a priority list. Each list has, each task in the list has a priority, which is chosen uniformly between 0 and 1. This is very important because this assumption of uniformity in terms of priority of tasks also assumes that we are not introducing heterogeneity in advance. Okay? So this is, we just select a random number between 0 and 1. That will be the priority of the given task. And then we can execute, each time we execute a task with probability p, we are going to execute the highest priority task. And with probability 1 minus p, we select the task randomly from the list. So if p is equal to 1, it means that we are running purely the third protocol. If p is equal to 0, we are running purely the second protocol. So by varying p, we move between completely random and completely determined by the priorities. Okay? So what happens that if we choose the random strategy, p equal to 0, the waiting time distribution is going to be an exponential. It means if p is equal to 0, that whatever I do is independent what I have done before, so I don't have correlations between things I'm doing. I have a random selection of tasks from the list. On the other hand, if I choose p equal to 1, so I always choose the highest priority task to execute, and I take another assumption that my to-do list can have an arbitrary length, which means that I have an infinite memory, which means it's not true. So arbitrary length of L of the list means that whatever number of tasks you have in the list, you are going to remember all of them. This is not true. I keep to remember between 15 to 20 tasks I have to do. If it's more than 20, I have to write it down, otherwise I will forget. Okay? If you assume that you don't forget, what you will have with p equal to 1 is that actually you will have a power law waiting time distribution with an exponential cutoff with an exponent 3 over 2. Okay? So remember, the different priorities were coming from a homogeneous distribution, and just by using a priority model with p equal to 1, we receive a power law waiting time distribution. In the other case, if I assume that I have a finite memory, so I have a finite priority list, it will be yet a power law, but with an exponent minus 1. Why is it cool? It is cool because once you take these two observations, that okay, with the finite memory, I have an exponent minus 1, with an infinite memory, I have exponent 3 over 2, and you go to the data, what you observe is that in case of activities, for example, web browsing, emailing, or library loaning, the waiting time distribution comes with a power of the exponent 3 over 2, while if you go with exponent 1, while if you go to, for example, looking at the mailing of people, like Einstein, Darwin, and Freud, it is also a good example for systems where you don't need the memory, because if you get it by post a mail and it is sitting on your desk, you keep remembering that it's on your desk, because after a while you clean your desk and you find the mail again. The waiting time distribution in case of mailing appears with an exponent 3 over 2. So it means that our two extreme case with fixed or arbitrary lengths of list can at once explain the two exponents what we observe in real data. Okay? Of course, at this point it was published by Borobashi. László Borobashi is one of the pioneers of the field. He got really excited. Usually he got excited when he observes a power law. And he started to talk about universally class, that all the human dynamical bursty pattern can be categorized whether to category with exponent 1 or exponent 3 over 2. Turned out it's not true. We have a lot of different exponents. But the model he proposed, the priority queuing model, gives a very good explanation. And now this is not only reproduction of data, because here we assume that things are correlated with each other, and assume that things have priorities, and gives an explanation why we observe bursty behavior. Do you have any question? Can mean three things: whether you understand everything, whether you are sleeping. I don't want to think about the third one. Yeah.
Why did they choose completely random pattern? So you have this probability P, in which you choose always the highest, and you want to introduce some randomness. Is completely uniform choice not becomes the priority you are saying?
I mean, the point what they wanted to prove with this p-value is that exactly the case of complete random choice, which belongs to the case when your actions are independent from each other, because you don't consider priorities, reproduce the Poisson behavior, where by definition the consecutive actions are independent from each other.
Did they study infinite case?
Oh, there is I'm writing a book on this. There are 64 papers only on modeling burst dynamics. So there are a lot of literature if you're interested. I can send you the list. Yeah. There are about 3 other paradigms. There is one major paradigm, the third one, which is based on memory and reinforcement, saying that this is actually, there is a model by Alain and Ginastra and Julia Stelle, where they assume that longer you do something, larger the probability that you remain to do something, and the contrary. So this type of correlations, introducing memory, is also another paradigm or another way of explaining burst effect. Okay? Very well. So if there is no question, I'm moving on the next subject, which is about the social brain hypothesis. There are several people from social sciences here, so I assume that they know what is the social brain hypothesis is. I'm sorry if they get bored. I hope I will be able to say new things about it. So the related literature is typically condensed around Professor Dunbar, who is a social anthropologist at the University of Oxford. He made the first observations of the first hypothesis. Actually, he made the social brain hypothesis. On some observations we are going to discuss. There are other papers related to this topic. We are going to discuss a little bit this one, which is an empirical verification using online social networks of the social brain hypothesis, of the Dunbar's number, and this one later, which is on another topic. Professor Dunbar really likes to write pop science books, so if you have sleepless nights, you can read all this. Okay? Very well. So what is the social brain hypothesis? The assumption here is that human intelligence did not evolve primarily as a means to solve ecological problems, but rather intelligence evolved as a means of surviving and reproducing in large and complex social groups. What does it mean? It means there are 2 ways we can look at this problem. One way is that actually our social capacities, think about social capacities as the number of people who we can meaningfully interact, is determined by our cognitive capacities and vice versa. Our cognitive capacities evolved in order to support social complexity. Okay? Of course, when you think about this, you can assign this to some kind of intelligence. People used to talk about intelligence assigned to human intelligence, which is intellectual capacity of humans, which is characterized by perception, consciousness, self-awareness, and volition. While, on the other hand, you can also define a social intelligence, which is the capacity of effectively negotiate complex social relationships. Okay? The question here is that our hypothesis is that our brain is complex because it's a very simplified, stilized sentence, what I'm going to say. It is not true like this, so don't shoot me, please. Our brain is complex partially because we live in a complex social environment, so the 2 has to be somehow correlated with each other. And this was the idea of actually Robin Dunbar, that he identified that there must be a consequence in case of primates, that the complexity of interactions characterized in social behavior of primates should correlate with their cognitive capacities. Okay? So now the question is that how to measure social capacity or social complexity and how to measure cognitive capacities. So in case of primates, social complexity can be very simply measured by the average size of social groups in what primates live. Observing gorillas in the jungle, see what is the typical size they live in, or other type of apes, to identify, how many social ties they can handle without splitting. How to quantify cognitive capacities? His approach was even simpler. You can just simply measure the volume of neocortex, part of the brain which is responsible for cognitive capacities. Okay? So once he did it for several apes, he found that the size of the neocortex is somewhat linearly or more or less linearly correlated with the average size of the social group in these apes are living in. Okay? It's a very simple measure. You can argue whether it's a linear correspondence or not. Coming from different distances, you may have different conclusions. What you can see that this is an increasing trend. So what Professor Dunbar did, he fitted a linear function of it, and of course the final question is, by knowing the human neocortex size, whether we can say the typical number of social ties we can handle. And by putting the neocortex size of the human, he arrived to the magical number of 150, which is called, from this moment, the Dunbar's number. The Dunbar's number is telling you, estimating, on average, a human, how many social ties can maintain at a given time. Of course, the neocortex size distribution of humans is not a power law. Otherwise, the Dunbar's theorem would not work. Why it is not a power law? We don't have a varying size of heads, so you don't have a friend with a 10 times larger head than you have, right? So it is a symmetric distribution. So human brain size can be pretty much characterized by its average, which means that this number should be universal. Well, whatever happens, as a human, you can handle about 150 relationships at the same time. This observation had been reinforced later by, for example, observing that in Neolithic farming villages, the size of a village was around 150. It was an early verification of the Dunbar's number. On the other hand, we have another observation, very contradicting, is that now we are living in the digital age. We are on the online social networks where we have 700s, 800s, thousands, 2,000 friends. Which means that it seems, because of online social sites, we are able to handle more friends than what Professor Dunbar projected, right? The question is it true or not? Is it true that the digital era helps us to go over our cognitive limits, which is there due to cognitive limitations? And in order to answer that, there was a group led by Professor Veszprémányi at Northeastern who tried to actually quantify exactly this question. More precisely, they asked how many stable social ties one is able to maintain without sharing attention. Okay? What they did is very simple. They went on Twitter. They had a very large Twitter dataset of 380 million tweets. And they extracted actually 25 million of conversation out of these tweets. And they actually recorded the following structure. If there was a person, let's say Alex, who posted something on Facebook, and there was someone who was commenting on his original post, they draw a directed link from someone to Alex. Then if Alex was commenting on the comment of his original text, Alex could appear in this tree once again. There was a directed link from Alex to the comment, and so on and so forth. So they could actually draw these directed comment trees around topics, around single comments, around single posts of people, just by following who was commenting on who at what point of the time. After this, they could do it for every post. So they had a large number of these comment trees. From these comment trees, realize that here nodes are people and links are comments on posts or on comments. So taking these trees, they could actually sum it up to a network, a directed weighted network, where nodes are people, links are directed, saying that how many times A was commenting on the post of B. Okay? Then there is another link saying how many times B was commenting on the post of A. In this network, it's a directed network. You can define in degree and out degree. In degree means how many links are directed towards A. Out degree, how many links are directed from A to somewhere else. And you can also identify the in strengths and the out strengths, which is the sum of the weights of the in links and the sum of the weights of the out links. Is that clear? Good. So then, by using this very simple weighted directed network, they could measure the simplest thing ever, which is the fraction of the total weight of a given node divided by its out degree. This actually omega I out is telling you what fraction of attention you are committing to one of your social tasks on average. Okay? So if we commit the same effort to everyone independent of our egocentric network size, if I'm increasing my out degree, this function should go linearly. It should increase linearly. If I have some capacities which are limited, it should behave in a different way. And actually what they observed is the second one, is that if you plot this omega out function as a function of k out, indeed in the very beginning it is increasing, so if you have 3 friends, if you have 10 friends, 20 friends, and so on and so forth, you commit 10 times, 20 times more attention to them. Each of them will get the same amount of attention. But after a while, magically around 150, this reaches a plateau, which means that you are not able to commit the same amount of attention to everyone. You have to start sharing your attention between people because you have cognitive capacities, you don't have enough time, and so on and so forth. And after that, actually, if your degree is increasing, your attention is going to decrease what you commit to people. Okay? So this was a very simple verification, if you can accept this as a verification, of the Dunbar's cognitive limitation, the Dunbar's number, saying that even you have on Twitter ability to get information or comment on thousands of people, effectively you can pay attention only on about 150 of them. Do you have any question?
It's not a physical limit, rather than a particle limit?
I don't know. It could be a time limit. There is a limit. That's probably we can agree on. Whether it is a cognitive limit, whether it is a physical limit, whether it's both or a time limit, I'm not able to say.
The question is still
in a way, yes, but since we know that there is a limit, we just have to learn what kind of limit it is. Okay.
You know that dirigent for music have a capacity to check different line of different instruments up to 20, and they learn to check the information in package. And it's not possible to package if the people are a bit the same or same group, and it's social communication like orchestra.
Yes.
Either.
So I have a bit of experience in this field. I'm a musician. When you are looking at a partiture, you have roles depending on the style of the music. It's Baroque music, classical. There are different patterns which are characterizing the piece of music. So actually what you may learn is these patterns. In case of humans, you may have patterns, but I think humans are very more stochastic than music. Yeah, if you listen free jazz too much, probably you have the opposite opinion. But I think patterns are, of course, we have to learn human behavioral pattern of people. Otherwise, we wouldn't be able to navigate in society. That's, I think, we can agree on. But there are no such strong unwritten patterns. For example, what is characterizing contrapunct in Baroque music. So things which are, you can guess, or you can, just by looking at it, you can sense what is written there. I don't know whether it is answering the question. Okay, there is another theorem, what is very fashionable to address in computational social science, what I would like to discuss, and after that we will turn to modeling to understand why we discussed all this. It is the Victor theorem. Probably you know the Victor theorem. Do you know the Victor theorem? So the Victor theorem has a really long history. I'm not even starting from the very beginning. It was 10 years in the 19th century who first talked about two types of social ties, strong ties and weak ties. Gesellschaft and Gemeinschaft, I think in German, these are the two terms. I start with from a Russian mathematician, Anatol Rapoport, who first talked about weak ties and strong ties, and he tried to understand how information is diffusing in a social network. His assumption was that if there is an ego, A, and the ego has one friend, B, and another friend, C, then the probability that these two friends are going to be connected is larger than chance. Okay? More precisely, if A is linked to both B and C, then there is a greater than chance probability that B, C, and it's exactly the same what I just told you. Okay, so it means that if I have two friends, there is a large chance that there will be a triangle among us. If you think about triangles, then you will arrive to the notion of communities, which actually consists of triangles. Okay, so that was, I think, the most powerful consequence, or the largest, strongest consequence of the assumption of Rapoport, that it was leading to the notion of communities. On the other hand, based on this idea, Mark Granovetter was going one step further. He's actually an amazing guy. We are going to discuss another model of him completely independent of this in the end of the lecture. He's a celebrated social scientist in computational social science, except that he doesn't give a damn. So he's not coming to any conference because he says that he exits this field. He's not interested anymore in weak ties. At the same time, there are dozens of groups who are trying to verify his theorems successfully. So his assumption was that as a consequence of Rapoport's claim, there must be a structure, a community structure emerging as such that those guys who are connected in triangles, so friend of a friend is my friend, those guys are actually connected by strong ties. These strong ties, the ones which are maintained by several interactions, and those people who are connected, who are belong to different communities, they are actually connected by weak ties, which are maintained by a small number of interactions. Okay, so actually his original motivation was how to find a job. Maybe through this example you understand it better. His hypothesis was that if I would like to find a job, I would like to have access to information that there is a new job opening. Just by communicating with the people from my own community, I may not access this information because we are so much connected that after a while we will just talk about the same thing. There is no new things coming in to the discussion. On the other hand, if I listen to my weak ties, so social ties which are connecting me to dissimilar people in other communities, I may have actually received information via these ties, even I'm just talking to them very infrequently. So his claim is that those communication ties or those social ties which are inside the communities are maintained by several interactions, but they are not so important in terms of information diffusion. On the other hand, those nodes which are in different communities are connected via weak ties. These weak ties are holding the whole structure together and are actually responsible for the global spreading of information. He even proposed the measure, the link overlap measure. It was actually proposed by Granovetter to quantify this assumption. The link overlap measure, I don't know whether you talked about link overlap measure earlier. It is the clustering coefficient of a link. It's very simple, simply defined. It is a fraction where in the numerator you take a link. In the numerator you count the number of triangles around this given link, which means the number of common friends of these connected people. And in the denominator you take the possible number of triangles, the possible number of common friends of these people. So if all the friends are common of the two guys connected by the link, overlap is equal to 1. If they have no friends in common, the overlap is going to be 0. in between the two, it assigns the fraction of common friends between two connected. Okay? So it's very simple, very cool. There are a few disadvantages of it. One is that it is bounded between 0 and 1. Second, it is strongly discretized because it is defined by the fraction of two integer number. And the third is that if you go to real data, it turns out that 50% or even more of the links used to have zero overlap, which means that you can say that they are all weak ties, but you cannot differentiate between them further than that. Okay? Yet, this is a very powerful measure, as I'm going to show you, can be actually used to verify the Granovetter's theorem, saying that those ties which are inside communities, meaning they have a high overlap value, are maintained by a larger number of communication, and those links which are between communities, meaning they have small overlap value, are maintained by a small number of interactions. To do that, we take a mobile communication data, where what we have individuals. These individuals call each other as a function of time, so we record not what they are talking about, just the action of that they call each other. So we have a temporal sequence of interactions. We aggregate this temporal sequence, and we say that two people are connected in the social network if ever they talk to each other, and the strength or the strength of that interaction is proportional to the number of interactions they have. So for example, there is a strong social tie between me and my brother because we used to call each other frequently, but there is a weak social tie in terms of number of communications between me and my dentist because I used to call him once per year. Okay? Very well. So once you have this network created, so for example these are different samples of this network, you can try to measure whether there is a correlation between the number of times two people call to each other and the overlap of that given link. Okay? To measure this, it's a little bit tricky exactly because overlap is defined as by two integers, so you cannot really simply look at the correlation. So there was a trick which was defined by Onnela and others who actually first observed this correlation. What they did, they sorted the links by their number of interactions, and they started to remove the link which had the smallest number of interactions, the second smallest, and so on and so forth, until they arrived to the last link which has the largest number of interactions. And what they did, they measured the average overlap of the links which remained after removal of this fraction of ties. And what they observed is that more and more ties, so only ties which had a really large number of interactions remained in their average, the overlap started to increase. Which means that more you call, larger the overlap on that social tie, which is actually the verification of the weak tie theorem. One side of it. Okay? If you do it in a randomized network where you randomize the weights on the network, but you keep still the community structure, the red line what you will receive, since you decouple this topology weight correlation, naturally you will not observe this increasing trend. You will see that whatever order you remove the links, the correlation is going to be flat. There is no correlation. And then the third measurement, actually they were measuring between a centrality of ties, showing that actually those links which have small overlap, so those one which are between different communities, have high between a centrality, which is expected as well. Do you have any question? Okay, they made one step further. So the second claim of the Granovetter's theorem was that weak ties are sitting between communities. So these ties are responsible to bridge information from one community to another community. So they are connecting the whole network together. So what happens if you remove them? And this is a typical percolation type of analysis. What they did, they took the network, again the mobile phone communication network, and they selected two strategies. In one strategy, they removed first the strongest tie, the second strongest tie, the third strongest tie. So in a decreasing order of number of calls. And the other strategy that they remove links in an increasing order of number of calls. Okay? And what they observe that if they start to remove, and this is the black line, with the strongest towards the small, the weakest, they saw that the network is keep remaining connected until they remove most of the links. On the other hand, if they start to remove first the weak ties, the ties which have a small number of interactions, there is a point where the network falls apart. Which means that actually weak social ties are sitting between communities. If you remove them, you will have disconnected communities in the network. While if you remove first the strong social ties, it's not happening because you remove these links from densely connected parts of the network. So overall, actually it remains connected. Okay? Very well. So using this very simple measure overlap, the correlation between overlap and number of interactions, tie strengths, we could actually empirically demonstrate the weak tie theorem. So now what we have in hand, that we have cognitive capacities which may determine the size of our egocentric network, and we also have this correlation that in a global social network, those ties which are maintained by a small number of interactions are between communities, these are the weak ties, and those ones which are maintained by a large number of interactions are inside communities, these are the strong ties. So now, next step, we are going to try to model it. Okay? Very well. Any question? I'm going to talk about this model, and then we can make a break. I think that's a good strategy. In order to model this, first we are going to make further observations using actually the very similar data than before. This is a mobile phone call dataset. This contains about 600 million voice call records. So again, not the content is recorded, only the action that A called B at a given time. It's over about 6 months, between about 6 million users in an undisclosed European country. It contains about 60 million links, and it is weighted by the number of interactions people have with each other. Okay, this is a very small sample of it. It's a single little town actually. Nodes are individuals, and ties are drawn if they ever caught each other, and the width of the tie is actually scaling the number of interactions they have with each other. So you can also observe that although this is a static representation of the graph of the network itself is temporal. What we have here is a sequence of interactions. So it is not coding per se from the very beginning. The structure of the social network, you have to integrate it in order to observe the social network structure. What you have here is a sequence of interactions, a temporal network. And our next step is somehow model this temporal network in a way that we have these correlations what we already learned about, for example, triangular closing by Rappaport and so on and so forth. We try to add these mechanisms into a very simple model of temporal networks to see what comes out, whether we can reproduce what we have observed in real social networks. So the model that we are going to use is called the activity-driven model of time-varying networks. It's quite recent, it's from 2012. The model itself originally does not make much sense, but we will try to make it better. It takes actually only one assumption, namely that people have different activity potential. What does it mean? It means that I may call 10 times per day, my wife may call 100 times per day. Her activity potential is way larger than me. She's way more active to call during a given day than me. So you can assume that there is this difference between people. Not everyone is calling the same number of times per day. Some people call more, some people call less. This is the only assumptions you have to make. Then the model is defined as follows. You take n disconnected nodes, and to each node you assign an activity potential. It will tell you that within a given period, how many events this node is going to generate. This activity potential can come from an arbitrary distribution, okay, whatever, at this point. Let's call it fx. Then the model is going down as follows. At each time step, you start with n disconnected node, and you ask each node, do you become active at this given time step? The probability that a node will become active is proportional to the activity potential. If the activity potential of a node is large, it will become active with a larger probability. Okay? If a node becomes active, it will select another node randomly from the rest of the network and make a connection, a call to this other node. If it remains inactive, nothing is happening with him, except if some other guy select him randomly. Okay? Very simple. So what you have actually snapshots of temporal networks, where at each snapshot you have social ties which appeared due to active nodes at that given time step. And in the end of each time step, you remove all the ties and you start it over again. So you can actually integrate or aggregate it over time, and you can receive, after a t period of modeling, an aggregated static representation of the graph, where you have ties between nodes if there was a link ever created during the simulation process, and the weight of the given tie is the number of times they contacted each other. Okay? Exactly the same as we could observe in the mobile phone communication. So if you play with this, what you will receive is something like this. First of all, one can prove that the degree distribution of the emerging network, so the aggregated network, is going to follow the same functional form as the original activity distribution, what you assume. What does it mean? It's a very, very simple claim. It means that if I am more active, I will have a higher number of degrees. Why? Because I will become active in more time step. I will connect random guys in more time step. I will have a larger number of larger degree in the end of the observation. So actually, the degree distribution, what we will observe in the end of the simulation, is coded by the activity distribution. So if we assume that our activity distribution is a power law, our degree distribution is going to be a power law as well. Okay? So this is what you observe. This is an aggregated network of the ADN model for a couple of time steps. It looks very random, except you see these hubs. These are the most healthy guys, which appears with the highest degree consequently. And you can also look at the different statistical properties. This first line of figures is coming from real data. So this is the real degree distribution of the mobile communication network. This is the real weight distribution of the mobile communication network. And this is the real activity distribution. If you look at the simulated network, you see that the activity distribution is broad, just as we observed in the original data. It is not a miracle because we assume that it is a power law. So at least so far we are good because we observe the power law. But you also observe that the degree distribution is also a power law, exactly because of this, since the activity distribution is coding the degree distribution. Okay? But what you also observe that there is a line here, maybe it's not really visible, that the weight distribution is an exponential distribution. Why? Because these nodes, active nodes, are connecting others randomly. There is an exponentially small probability that they will, by chance, connect someone else. Okay? That's why the weight distribution is actually an exponential, despite our empirical observation, which is a broad distribution. So now, next question, what can we do in order to recover this observation by using this very simple model? To do that, we are going to play a game where we have an ego in the middle, and these are the people who we can observe this ego to interact with. Okay, so these are the potential friends. And we start to observe how the ego is interacting. First, we see that this ego is calling this guy at one point, which means that the degree of the ego is going to increase from 0 to 1, and there will be a social tie assigned between these two guys with the weight 1. Okay? Then later on, the second call of the ego is towards this guy, which will increase its degree again by 1, so it will be 2, and the link weight is going to be 1 again between this guy and this guy, and so on and so forth. On the other hand, we can also observe that this ego may recall someone, contact him or her again, which means repeating an interaction, which means it will not increase the degree, because we already observed the social tie, but will increase the tie strength, the link weight from that given tie in our observation, and so on and so forth. Okay? So after this, what we can do, we can actually define a very simple probability, which tells us what is the probability that by observing an ego who has already n number of connections, degree, what is the probability that the next event, next call, what this guy is going to do, is going to be towards someone new, or towards someone who he or she has already contacted before. Whether it's a creation of the next mobile call is going to create a new social tie, or going to reinforce an already existing one. Okay? Again, there is this paper by Alain and others who are using very, very similar reinforcement type of mechanism to explain a slightly different phenomena, but the idea is very similar. So actually this Pn probability can be measured from data. If you do that, what you see, you measure it for different nodes who have degrees, different degrees in the end of the observation, because you don't want to compare people who has 2 friends to people who have 200 friends. But what you see that for each of these people, so for example, guys who have at least degree 128 in the end of the observation, the Pn function, this probability, is decreasing, which means that more friends you have, smaller the probability that you are going to create a new social tie, and larger the probability that you are going to reinforce an already existing social tie. It's important that you understand this. It's important also to relate this observation to cognitive capacities, because this is actually due to cognitive capacities. You cannot have infinite larger number of friends, but at the same time you keep remembering who your friends are, and you repeat interactions with them after you have enough of them that you cannot have more. Okay? More friends you have, smaller the probability that you will have a new friend. Professor Dunbar went one step further with this claim. He has this interesting paper where he shows that if you break up with your girlfriend, you will gain 2 friends. So here he has this causal relationship between in the egocentric network evolution. Very well. So what we see is that this is a decreasing function for any type of nodes, independent in the end of the day how many social ties they will have. Moreover, we can actually fit these functions with a very simple functional form, and using this we can scale them together, showing that they are all fitting on the same theoretical curve with a very, very simple shape, pretty much 1 over n plus 1. We have an offset parameter c, which can be very, very useful later, because this simple functional form can be right away integrated in our activity-driven network model. If you remember, in the network model, our decision was that every time I become active, I call someone randomly from the population. So now, instead of doing this, we say that if I become active, when a node is active, it will connect with the Pn probability someone randomly from the population, and with the 1 minus Pn probability, will contact someone who he or she has already contacted before. So repeat an interaction. And as we already also see, as n is increasing, the probability that I'm going to call a random person is decreasing. Okay? So there will be a slowing down of the egocentric network evolution speed. Okay? Everyone is tending towards a fixed number of interactions, which after they will have just a marginal probability to increase the egocentric network size. They will most of the time try to repeat interactions with already existing neighbors. So it is a very simple extension of the model, right? On the other hand, if you look at what it causes is very striking. This is our previous observation. Once we add this reinforcement process of social interactions, what you see is that there is a way more structure in the emerging network structure. You see still there are hubs with large number of interactions, large degrees. On the other hand, you see that there are ties with large number of interactions. So unlike here, where you have exponentially small probability to repeat an interactions between the same people, due to the reinforcement, nodes actually tend to start to repeat interactions in already existing time, which is causing actually a weight heterogeneity emerging in this process. What you can also see from data, from simulations, so what we observe here, the activity distribution is still the same because this is a parameter. The degree distribution, which is in our model network with memory with reinforcement, now is the solid red line, is very similar to what we observed in real data. It is, the exponent is larger, the distribution is steeper, there are smaller degree heterogeneities, exactly because after a while the eccentric evolution, network evolution is slowing down. Okay? But the exponent is actually pretty much the same as what we can observe in the data. And more strikingly, the weight distribution becomes parallel. Before it was an exponential function, exponential distribution. Now that we added this reinforcement process, we push nodes to repeat interactions instead of creating new ties. The weight distribution will become a power law very similar to the empirical observations. There is another important consequence of the reinforcement process, namely that if you measure the largest connected component of the network, how it is evolving as a function of time, due to this reinforcement, it will slow down. Why it is important? Because there is no collective phenomena which can emerge faster than the evolution of the largest connected component of the network, which means that this reinforcement process, which seems to be very real because, first of all, we observe in data, second of all, it gives us a very nice fit. It's not even a fit, very nice emerging property which is fitting on the original observation, causing us a slowing down of the connected component. So it has to have an effect on any dynamic processes, starting from opinion dynamics, epidemic spreading, whatever you want. Very well. So where are we now? We have a temporal network model which can have degree heterogeneities, very well, which can have weight heterogeneities. This is our last achievement. But yet we have that this network has no community structure, and moreover, it doesn't have this weight topology correlations, which was claimed by Granovetter, the weak ties. Okay? So the next step is, what do we have to add to this network model? That it can reproduce communities or community-like structures. Of course, it's a model, so it will not reproduce real communities, just something which look like communities. And the weight topology correlations. To do that, we are going to think about three mechanisms. One is called the link closure process, which is very logical. Actually, what happens is that when there is a node who is active and decides to create a new social tie, it will not do it randomly, but will try to close a triangle. Which means that it will run a local search, look for a friend of a friend who is not connected to the original active guys yet. If it is the case, with the probability p delta, it will close the triangle and reinforce the links visited during the local search. So this is when you go to a party of your friend and you meet a friend of a friend and you become friends. Another type of link creation process is what's called focal closure. This is the case when you are traveling on the bus and you become a friend with a stranger. Okay, so this is exactly what has been used before. This is the case when a node becomes active and selects another friend randomly from the rest of them. Okay? So if you distinguish between these two types of link creation mechanisms, we may have emerging weight community structure. At the same time, we could also expect that there might be weight topology correlations, because as I told, if there is a link is visited during the search of a triangle, that link is reinforced with an increment. Plus, we also try to recur the problem of the original model. The original model has n number of nodes, and then we are forever adding links, so it is actually going towards a fully connected network. So how to cure this? We introduce a node removal process, which means that there is a fixed probability, PD, which is telling us that a node is dying at a given time step or not, which means that we remove the nodes, cut all its links, and put it back right away, that the network size remains constant. Good. So what happens if you assume this mechanism in addition to the ones we already had? The network will look something like this. You see that this is evolving as a function of time. You see that there are actually emerging communities. Okay? And as we will see later, even weights are behaving as we would like. Very well. This is not a good visualization in a sense that this is actually not the temporal network visualized, this is the evolving network visualized. Here it's, you just see that a link is created, you don't see the repeated interactions on a given link. Okay? The first thing what we would like to see is that now we have this node removal process, whether the network is reaching a stationary state where we can make observations about this structure. Stationary state means that its general network properties became invariant of time. The first thing what we can measure is the average degree of the network, and as we see that as a function of this deletion or death probability, we will arrive at a stationary state where the average degree of the network is constant. The dashed line over here is assigning the average degree of the empirical mobile communication network. So this is the data. Okay? We can also look at the clustering coefficient of the network, how it is changing as a function of time. It has an initial period. This is belonging to the phenomena in the very beginning when you create a lot of triangles. And after a while you created the triangles, the Pn probability became small enough that you are not creating new social ties, so that the clustering coefficient is going to a constant value. So it is also becoming stationary as a function of time. And we can also explain this a little bit better just by looking what fraction of the nodes, what fraction of the link creations are belonging to reinforcement or new link creation. And you see that in the beginning all the links, all the interactions are creating links, and later on most of the interactions are reinforcing links. It also becomes a stationary property of the network. Very well. This so far is not very interesting. What is interesting is that when we look at the network, by varying the p delta triangle closing probability, we see that for p delta equal to 0, we have a random structure, which means always that link creation mechanism plays a role which selects randomly in the network. But when it is very large, we actually have communities emerging in the network. Also, don't forget, this is not a static network. This is just a static visualization. It's a temporal network. Okay? So we can actually quantify these properties. Its properties, we see that we can scale this probability as such that the network can actually have the same average degree as the original network. We can look at the degree distribution. It is fitting very, very well in the empirical data, which is the black dots. And we can also look at the weight distribution, which is also considerably close to the empirical data. Very well. So, first challenge, we have communities done. Second challenge, what if we change the reinforcement parameters? So when I'm visiting or repeating an interaction on a given link, how much I'm increasing the tie strength of the given tie. If it is 0, it means that I never increase. It is set by a default 1. If it is large, it means that for those ties where I'm repeating a lot of interactions, they will pop up and they will have a larger weight. And indeed, you see that in this case, you have again, as a function of delta, you can receive communities where the strong ties, which are the blue ties here, are going to sit inside the communities, which is exactly the big tie, the claim of the big tie theorem. You can again measure different things. You can measure the clustering coefficient. You see that you can select parameters which fits the original data. More importantly, you can measure exactly the same correlation between the number of interactions and the overlap. And you see that in the model, you see positive correlations, just as it has been observed in the mobile data and was hypothesized by Granovetter. And this is a residual clustering. It is not interesting too much. Okay? So all in all, we had these very general observations about cognitive capacities, about correlations between structure and tie strengths, and then we came up with a very simple model, which was originally not making much sense because it was generating random networks. But by adding a memory process, the two types of distinguishing between two types of link creation mechanism and node deletion, we can actually receive a temporal network which looks pretty much reality. Good. I would like to make a break now. And in the second part of the lecture, we'll talk about social contagion. So, now we addressed already two levels. I wanted to address the individual level dynamics, and also we addressed egocentric network dynamics to see how different mechanisms can drive to global network correlations. So the next level I would like to discuss is some global phenomena, and I chose the example of social contagion processes to see how we can actually model spreading dynamics in terms of social contagion on a network. If you would like to look at the literature, there is a great paper by Granovetter, of course, which was one of the first papers on social contagion. But later we are going to also discuss other social contagion models defined by Butts, for example, or the seminal paper of Duncan Watts and some more contemporary papers actually published by my group. So in order to start, the first thing I would like to quote actually a baseball player and commenter, Rex Hadler, who told that everything is contagious in baseball. Only thing what I would like to correct in this is that he was not precise enough, because I think everything is contagious. Okay, so this is the point what I would like to discuss. Do you have any idea about what is a social contagion, or some examples of social contagion phenomena?
There is some mode, I don't know, but there is some trend, so people make a behavior in like the trend said, and their social network of strong or maybe weak tie, depends on, make the same comportment according to the trend. Yeah.
Other examples?
Vestimentary habits, I don't know, you give us an example for obesity, but it's a very surprising results. So there is a lot of results, I guess.
Do you want to discuss the obesity case? I have slides on it. I just wanted to skip them because of time. We will see when we will get there. So I collected also a few examples of social contagion phenomena. The very first example I found was actually a book by Goethe. The title is The Sorrow of Young Werther. It's a very sad book. It's about a guy who gets suicide. And it is so sad that people read and they got suicide, so much that actually after a while it was banned in Europe. Okay? Another good example, it's not because I'm Hungarian, but this Hungarian guy wrote a song called Gloomy Sunday. Maybe you know the song. It was a hit during the Great Depression, beginning of the 20th century. And there was an urban legend that if you listen to this song, you will get suicide. I listened to this song, I'm still here, so the legend expired, let's say it like this. So it had such an effect that it had to also be banned from the radio, because there was a suicidal wave due to this song, or claimed to be due to this song. So actually social contagion is based on the assumption that different behavioral patterns can be identified as something which is spreading in society, something similar than an epidemiological case. Okay? The condition here, in case of epidemiology, the condition is that infection spreading can pass between people who are in touch, who are in contact with each other. In this case, this assumption also holds. There must be some relationship between people in order to influence each other, that they can pass or influence the other to do something similar than the original person did. Okay? These are very early examples. There are also more contemporary examples. For example, the iPhone. Okay? So one large factor in the success of Apple products is due to social influence. Saying that because my friends are doing something, because my friends have an iPhone, because my friends have an Apple computer, there is a pressure from my friends towards me that I'm going to buy an iPhone or an Apple computer. Okay? So typical examples, only, of course, not only Apple products, but in general adoptions of new products or new inventions. But you can think about information spreading as well as a social contagion phenomena, like, for example, spread of hashtags on Twitter or spread of rumors in a society. Or you can also think about behavioral spreading. People used to associate with social spreading the emergence of riots or the emergence of revolutions. Or, for example, as you mentioned, there are some studies which claim that even obesity can be identified as a social spreading phenomenon. When we talk about social spreading, there are typically two very important mechanisms what we used to discuss. One is what I already mentioned, social influence. So social influence is a force what people practice on their friends in order to force the other to become more similar than they are. Okay? There are typically two types of social influence. One is social influence. So this is the ability of groups to put social pressure on someone to become more similar. Or there is the interpersonal influence. Typically in high school, the coolest guy dictates how you should dress or how you should behave. So there is a highly regarded person in the social group who dictates norms or behavior patterns what the others are following. This is one very important mechanism. There is another mechanism which used to be associated to social spreading, though it's very important that we distinguish between the two, and this is homophily. Homophily is not a forced mechanism. Homophily is a selection mechanism. It is actually it's a mechanism to create ties between people who are similar to each other. So homophily means that those people who share some similarity in some sense will have a social tie between them larger than just. For example, the best example I can give, I was listening to the radio like 10 years ago about statistics about my generation, saying that my generation in Hungary, only 10% of them have university degree. Then I was thinking that 90% of my friends have university degree. So this means two things. First, homophily is real. The second, I don't know my generation, right? So this is exactly, homophily means exactly this: birds of a feather flock together. The probability that there is a social tie between similar people is more likely than between dissimilar people. There are other mechanisms which, so why is it important to distinguish from social influence? It is not because they are the same, but it is because it's very, very difficult to distinguish them. So for example, when I see that I buy an iPhone and I have already had a friend before who had an iPhone, it could be because he was or she was influencing me to buy an iPhone, or it could be because we are both interested in the iPhone. We have a homophilic relationship. We are connected because we are similar, and independently of each other, we bought an iPhone. So when you just observe a social spreading phenomena, it is very difficult to distinguish between the two because you don't know which comes first, whether link creation or the social influence. There are other mechanisms what you can associate with social influence. One is environmental effects. Like, for example, when it is raining, everyone opens an umbrella. It is not a social spreading phenomenon, even it looks like a social spreading phenomenon, because it's a collective phenomenon, everyone is doing at the same time the same thing. On the other hand, it is dictated by some external effect. You can also think about social identity. So this is a case when you are a part of a group and you would like to become similar or you would like to become dissimilar to the group in order to increase or decrease some dissonance between your social being and the rest of the team, rest of the group. You can also think about local information. When you observe a social spreading phenomenon, local information is the case when you are making decisions based on information what you receive only from your social environment, but not without knowledge about the whole society itself. Which means that locally you can make an optimal decision to follow, for example, a riot because you see that 90% of your friends are doing, but you are not looking at the whole society, maybe what you are doing is safe. Okay? And finally, we can talk about social exclusion. This is the case when you are I really didn't want to go to the examples towards Trump. But for example, Trump is a good example, is that some people join to support Trump because they saw that the things are moving in one direction, so they were afraid that if they don't move in this direction, they will be left out from something. Okay? So this is what's called social exclusion. In the modeling of social contagion, most of these mechanisms are not considered. The most important mechanism, social influence, which is usually in the focus, and what is claimed to be responsible for the emergence of global behavioral pattern. There are two types of model groups, or two types of models, what we can discuss here in order to describe social phenomena, social diffusion. One is the bus diffusion model. Have you heard about the bus diffusion model? So it was the observation of Everett, Rogers, and later Bus when they were looking at how people adopt different products as a function of time. So this is a very famous figure which was published, I think, in the New York Times, where they show that in the United States, what fraction of the population have had adopted a given invention, for example, bought a car, or a refrigerator, or a stove, or an air conditioning, or, for example, have internet connections at home. What you see here is that they are they evolve as a function of time in a very different way in the microscopic scale, but all in all, they all follow an S-shaped curve. Okay? What is the difference is the speed of the spreading itself, actually, that, for example, cell phones were adopted very rapidly after they were available, while, for example, electricity took about 50 years that penetrated in the society. But all in all, they all evolved through an S-shaped adoption curve, assigning some universal pattern how inventions or how products are adopted in society. So this was the motivation of Rogers and Bus to set up a very, very simple model. Rogers started by categorizing users in different adopters in different ways. He told that there are 5 different types of adopters. One's called innovators. These are the guys who adopt something without necessary external without social influence, but because they are interested in the product. So typically these are the guys who are queuing in front of the Apple store before the release of the new iPhone. Then there are people who is called early adopters. They are the ones who follow the social influence of the innovators, but they are also interested in the product. They are the ones who come right after the innovators adopted the product. Then there are the early majority, late majority, and the laggard. As you go by time, you can identify the period where people adopted the product, that you can categorize them in these different categories. On the other hand, Bus had a very simpler categorization. He had only 2 categories, innovators and imitators. So innovators, those guys who adopt a given product without social influence, and imitators are those ones who follow the behavior of innovators, who copy the behavior through the effect of social influence. So in his model, he made few assumptions. The first, that he tried to model a product adoption, which was a first product purchase, so it is not an update of an earlier bought product. Okay? He was trying to capture single user adoption. He was trying to capture a single product category, which means that he was not trying to capture iPhone 7s, but the adoption of mobile phones, for example, and assume that there is no production capacity for the product, so it is always available as much as it is needed. Okay? His model is very, very simple. It is actually described by a very simple diffusion equation, where on the left side what you have is this is the probability of adoption at a given time, that the adoption has not occurred. So F is the number of new product adoption at a given time, M is the size of the population, and N is the cumulative number of adopters up to a given time. So this is the probability that there will be an adoption at a given time point. On the right hand side you have two terms. The first term, the P, is actually the representing the innovators, okay, so people who are adopting by chance independently without social influence, while the second term is proportional to the coefficient capturing the fraction of imitators, people who adopt due to social influence, and it is of course larger the number of adopters in the network, larger the social influence the imitators we receive, larger the term, the second term in the equations. Okay? So if you simply solve this problem, you will receive a solution which has an exponential outbreak, and it is actually saturating to a given point. The data what I'm showing here, it is the adoption of a single product in Skype. It's a single one online service of Skype, like let's say that you can buy credits to make phone calls. You see, so the data points are the black points, and the red line is the bus model which has been fitted on the data in order to predict what's going to be the future of the given product. What fraction of the users are going to adopt, how long the adoption is going to go on, and so on and so forth. So just you see that by looking at a very simple example, a simple product, just by looking how many people adopted that product as a function of time, and assuming this very simple called simple contagion phenomena described by this diffusion equation, you can find considerably good fit on the data and make some predictions. Mathematically speaking, your prediction becomes way better after your product reached the inflection point, because the inflection point determines the speed and the final volume of the spreading behavior. So this was the first model which has been proposed in order to capture social spreading phenomena. There is another model set related to rumor spreading models, which are trying to capture a slightly different type of phenomena. Here it is information diffusion. Rumor spreading models are defined very similar to SIR type of models. I don't know whether you know what is an SIR model. SIR model, it's a model in epidemiology, where you assume that people can be in three distinct states, whether they are susceptible, infected, or recovered, and there are rates in which one person can become susceptible to infected and from infected to recovered, depending on network structure, number of interactions, and so on and so forth. Here we have three distinct states. We assume that people can be ignorant. Those are who are not aware of the rumor yet. We can also assume that there are people, after they heard about the rumor, they start to spread the rumor, so they are in a spreader state. And we can also assume that people who have known about the rumor, but they realize that it is not interesting anymore, they are in the Stifler state, which means that they are not spreading the rumor anymore, but they cannot be infected anymore as well. There are two models proposed to this type of dynamics. One is the Mackey-Thompson, the other is the Delay-Campbell model. They are very, very similar. Only different. So how it works is that both model describes if an ignorant person is talking to a spreaded person with a given rate lambda, they both become spreaders. If a spreader person is talking to a Stifler person with a given rate alpha, they both become Stifler. And if two spreaders is talking to each other with a given rate, one is becoming a stifler, the other is remaining the spreader. The difference between the two models is just the last term. In case of the delay-Kendall model, if two spreaders talk to each other with a given rate, they both become stifler. The social realm behind this, if I'm spreading the rumor and I tell to my friend and realize that he or she also knows this rumor, we both stop spreading because we realize it's not interesting anymore because it seems we all know about it. Okay? Also, this is the difference between so this last scheme makes difference from the SIR model, because in case of an SIR model, if an infected node is talking to if there is an infected node, this infected node can become recovered with a constant rate without even interactions. So, what is the difference more from the pathogen contamination? First of all, the spread of information is an intentional act. So I cannot become infected by an information just by chance, just by traveling on the metro. Okay? If I'm traveling on the metro, maybe I get the flu, but I have to talk with someone in order to get the information. Another difference could be that while in case of biological spreading, infection is an immediate act, in case of information spreading, you may need time and reinforcement in order to decide whether you accept that given information to be valuable enough to spread it forward. Finally, the act of adoption needs more than one exposure. In case of social spreading phenomena, not like in epidemic spreading, where epidemic spreading, actually a single stimuli could be enough if the rate is not zero, that you become infected. Very well. So actually you can describe this type of models with a couple of differential equation system. I don't go in very much into the details. The only difference from an SIR process is this term. It's a nonlinear term, which is actually causing a radical difference in the solution. In case of an SIR model, an epidemiological spreading, there is a critical point defined by the fraction of infection and recovery. If this fraction is smaller than a given value, the infection will die out. If it is larger than a given critical value, the infection will become will spread in the society and will reach a stationary state. In this case, there is no critical point. In case of the two rumor spreading model, even for a critical point very, very small, close to zero, you will have a spreading to spread all around the given population in every situation. Okay? So there is no critical point in case of rumor spreading models, as it has been actually demonstrated already. Very well. This is a very, very simple assumption. It assumes a direct correspondence, almost a direct correspondence, between epidemic spreading and social spreading. On the other hand, we may realize that there are further differences. Actually, this is a very important point here. The act of adoption needs more than one exposure, which makes a large difference between social spreading phenomena and epidemiology. And this has been actually addressed by complex contagion phenomena. The definition of complex contagion came pretty late. It was in 2007, although models has been proposed in the 60s already. It was Damon Santel and Michael Macy, who has a nice paper on complex contagion, where they actually formulated that phenomena in social networks in which multiple sources of exposure to an innovation are required before an individual adopts the change of behavior. Which means that they are discussing that every people has an intrinsic threshold which determines how open they are for that given innovation, let's say. Which means they are defining a threshold. If a smaller fraction of my friends tells me that this is a good product, I'm not going to adopt. But at the moment where a given fraction of my friends reach this intrinsic threshold, I will necessarily adopt the product. Okay, so for example, if my threshold is 0.9 in terms of buying an iPhone, it means that 90% of my friends have to have an iPhone to force me intrinsically to buy an iPhone. If it is only 89%, I will not buy an iPhone. At the moment it is reaching 90%, I'm going to buy an iPhone. Okay? So this threshold is an individual intrinsic variable determining whether you do something or you don't do something, depending on the social influence coming from your egocentric. Very well. Examples are diffusion of innovation, strikes and riots, and so on and so forth. So all the examples actually I explained before. The first model which has been proposed in this direction was done by Granovetter in 1978. The model was inspired by the classic Schelling model, and it is a binary decision model in order to describe how a riot emerges in the society. So Granovetter's assumption was very simple. He assumed that, let's say that we have 100 agents. He doesn't even assume that these agents are connected in a network, but he assumes that each agent knows what the rest of the agents are doing. So it is an unstructured population. Okay? He also assumes that each people has a threshold. Let's assume that this threshold is distributed as such that there is exactly one person in the population who has threshold 0, one person who has threshold 1, one person who has threshold 2, and so on and so forth till 99. What does it mean? It means that the guy who has the threshold 0, he needs no social influence to join the riot, right? Because he needs no friends to do something before he does, because his threshold is equal to 0, which means that he is going to initiate the riot. Then there is a second guy whose threshold is 1, who will see that this first guy with the threshold 0 has already joined the riot, and his threshold is 1, so he's going to join the riot, and so on and so forth. In the end of the day, everyone is in the riot. Cool. What if we change slightly the threshold distribution and assume that now the distribution that we have a person with threshold 0, another person with threshold 1, another person with threshold 3, 4, up to 100. So the threshold distribution is not continuous in that sense. What happens here is that the first guy with threshold 0 is going to join the riot. He is going to initiate the riot because he needs no social influence. This guy who has the threshold 1 is going to join the riot because this guy is already in. But this guy needs 3 friends in order to join the riot. But there are only 2 who join the riot, so the riot will not emerge. There will be only 2 people on the street. Okay? Which means that a marginal change in the threshold distribution controlled or changed dramatically the collective phenomenon. Okay? So it also shows that the threshold distribution of people matters a lot when we try to address the social spreading phenomenon. He also generalized this idea. It's a second approximation where he still assumes an unstructured population. But here, instead of distributing thresholds this way, he assumes that threshold values are sampled from a normal distribution bounded between 0 and 100 with a given threshold, standard deviation. And now the parameter is the standard deviation, is the homogeneity or heterogeneity of the distribution. What he showed is that by increasing the standard deviation, if the standard deviation is small, there will be no riot, and there is a critical point, which after everyone is going to be on the street. Okay? It is exactly the same as I explained as the first approximation, just here, instead of taking this homogeneous distribution of thresholds, he is playing with the standard deviation of it, demonstrating that an I always problem small change. I have always problem with this word, but I think since I was born, even a very, very small change in the standard deviation can induce radical change in the collective behavior. Good. Where is the problem? What is the assumption here which is not realistic?
we can class people who with a very precise probability of John or Harriet, or make a.
We can do what?
We can sort people with very precise, I don't know, very fine probability done, then make the compartment. So there is a big assumption.
There is a big assumption about the threshold distribution itself, but this is not what I'm asking for.
There's two things. One is that they know the overall reactions to the right, and the other one is that there is no structure.
Exactly. So this is what I'm talking about. That it is an unrealistic assumption, first of all, that you know what the whole population is doing at the same time. The second, he is not assuming that there is a social network, right? It is an unstructured population. So if you think about a social network, it will radically change everything, because then fractions are not going to be compared, or thresholds are not going to be compared to the whole population, but only to a egocentric network. And this was the main contribution of Watts. First of all, they identified that the threshold is not only, it's an intrinsic variable, but it is depending on many other things. It is mainly depending on a personal utility. So you may have advantage or disadvantage to do something or not to do something. Of course, you're optimizing in this, which will in turn will determine your threshold. And it is situation specific. So my threshold, for example, to join a riot might be different than to buy an iPhone, for example. Okay? It's very different. The other main contribution of Watts was to identify that there is a strong effect of the network itself here. Because thresholds are defined as fraction of friends, necessary fraction of friends to do something, necessary fraction of friends who have done something in order to force me to do something. So it is determined, but so strongly influenced by the number of friends I have. So for example, if I have 100 friends and my threshold is 0.5, it is very unlikely that I will have 50 people in my egocentric network to doing the same thing as compared to the case when I have 2 friends, right? I will have a larger probability that one of my friends is doing something, reaching my threshold, forcing me to do something. It is exactly 0.5 as well. Okay? So, in order to model this, Watts proposed another categorization of adopters. He was categorizing adopters in 3 different sets. The first, what he called innovators. These are the guys who have a threshold 0. So the ones who need no social pressure or social influence in order to adopt something. They are the ones who are spontaneously adopting the product, the idea, the behavior, and so on and so forth. Then he identified vulnerable nodes. Vulnerable nodes are those ones who need exactly one neighbor to do something, and they do right away. Which means that their threshold is 1 over their degree. Okay? They are vulnerable because they don't need large social pressure. If I'm a friend of a vulnerable and I do something, my vulnerable friend is going to do exactly the same. And the third category are the stable nodes, those ones who need more than one friend. So their actually threshold is larger than 1 over k in order to adopt or behave in the same way. Which means, so they need not only 1, but 2 or 3 or 4 larger fraction of friends, larger number of friends, in order to adopt. Okay? Very well. So if we differentiate these 3 categories, we can arrive to a model which is really fascinating actually. It is defined as follows. We take nodes which are connected in a network with an arbitrary degree distribution with an average degree z. Okay? We assume that there is a network structure. Then we assign a threshold to each node in the network coming from an arbitrary distribution with an average threshold phi. Okay? It's also arbitrary. We assume that in the very beginning, no one is an adopter, everyone is in a state 0. And actually, we also assume that once someone adopts what we are interested in, it will switch its state from 0 to 1 and it will remain there forever. Okay? So it's a binary dynamics with an absorbing state if you are a physicist. What we do first is that we give the adoption, we assume that there is one single innovator in the whole system, which means that this is the only guy with the threshold equal to 0, which will spontaneously adopt the product. And then what we are interested in, how the adoption spreads in the network. So this is the game. We have the network. We have the 3 types of nodes. Green is our single innovator, blue are vulnerable, and yellow are stable nodes. We initially assume that the innovator is adopting the product due to external influence spontaneously. If it is connected to a vulnerable, the vulnerable guy will immediately adopt the product because it needs exactly one neighbor to do so. Exactly one adopting neighbor to do so. In the second step, and this is a very important and very, very restrictive condition, if this vulnerable guy is connected in a vulnerable tree, the whole tree is going to adopt the product immediately as well. Why? First of all, why it is a tree? It is a tree because if it wouldn't be a tree, there would be a guy who is not an innovator. Okay? So, how it goes? After the tree adopted, there will be some stable nodes whose threshold has been reached and they are going to adopt the product. Okay? So how it goes? Initially, there is an innovator is connected to a vulnerable is connected to a large, what's called percolating vulnerable tree, which will immediately adopt the product, which will push further stable nodes to it. Okay? It is very cool, very restrictive. What he was actually showing is that the condition for the emergence of a global phenomena is that there is a percolating vulnerable tree in the network. What does it mean? It means that there is a large fraction of the network consists of vulnerable nodes who are connected together with the tree. It will spread all of a sudden in the whole network immediately and will cause second and third wave of innovation. But without this tree, if assume that, for example, these 2 guys are not connected, our adoption process will be unable. If we have this tree which is spreading all around the network, consists of innovators who need exactly one neighbor to adopt, once one of them is adopting, the whole tree is going to adopt at the same time. Okay? So for observations, he just set a few parameters. First of all, he identified a global cascade. If the cascade reached at least 20% of the network, this is an arbitrary choice, could be 90%, 50%. The other, he identified 2 control parameters. One control parameter was the average degree of the network. The other control parameter was the average threshold of the nodes. And what he was looking for the average size of the triggered cascades as a function of the average degree and the average threshold. Okay? The system, what he was using, he used a uniform random graph with an average degree z. He used a delta function for threshold, which means he assumed everyone has the same threshold. It's very unrealistic, but for modeling assumptions, this is the simplest case what you can do. And when he was initiating the process, he was not using one single seed because the network was too large. He used a small number of seeds who were far from each other. Okay? What he observed is this. This is actually the phase space as a function of the 2 control parameters, average degree, average threshold. It has 2 phases. In this phase, the blue one, there is always a global cascade emerging. In the green phase, there is no global cascade emerging. I can translate. In this phase, there is a percolating vulnerable tree in the network. In this phase, there is no percolating vulnerable tree in the network. Moreover, he observed that the phase boundaries of this phase space are very specific. This boundary, this is as you are increasing the average degree of the network, the system goes through a second order phase transition. This can be easily understood. Why? Because in order to have a global phenomena, I already mentioned you need to have a large connected component. And since the network itself, it's an Erdős-Rényi non-random network as a function of P, probability of connection, the network itself is going through a second order phase transition, exactly like this. If the average degree is very, very small, you have only small connected components in the network, so you cannot have a global phenomena because the largest phenomena is actually equal to the size of the largest component of the network. But as you are increasing the average degree of the network, you have a large component emerging in the system, which means that your largest cascade, largest social spreading cascade is equal to this size. As the size of the largest component is increasing, your possible size of cascade is increasing as well. So in this case, to the lower limit, the transition between the phase where you cannot have a social spreading global phenomenon to the phase where you can have a global cascade is controlled by the connectedness of the backgrounding network. This is one phase transition line. The other phase transition line, this one, it's even funnier. This is the first order phase transition line. And why? This is actually the case when you have your threshold, let's say 0.2 for everyone, but the network is getting denser and denser. At some point, you will have too many neighbors that you can never satisfy your threshold. Which means that from the phase, at the critical point of density, from the phase of cascade, global cascades, you will enter to a phase where there will be no possible global cascade. Okay? You can actually further quantify this. You can look at the cluster size distribution or cascade size distribution, and as you see that as you are going, so this is just demonstration where these four figures are belonging to, we are going towards, for a fixed threshold, we are going increasing the average degree of the network, and the four lines are the four green lines over here. If we are below the first critical line, we have an exponentially distributed component size because the network is disconnected. At the transition point, which is actually equal to average degree, excess degree equal to 1, we have a power law distributed cascade size. And once we enter this system, we always have small components and have a large cascade. Why it is not a single point? Because it's from several simulations. Okay? The other phase transition line, we are inside the cascade regime. It means that we have large cascades. We are increasing the average degree. At some point, we will lose the largest connected component because the system has this lock, becomes too dense. Then the component size distribution will become exponential. Okay? I skipped here a few slides, but I can show you it even better. If you look at the average global cascade size, this is the lower transition line, which is a soft second order phase transition, and this is the upper phase transition line, which is a hard first order phase transition. You can also look at the frequency of global cascade, which will show you the same. Moreover, you can look at the time the system needs to reach the maximum size of the cascade, and you see that there is a critical slowing down at the two phase transition. Okay? Very well. So this is a very, very nice model. It's changed a lot, or it contributed a lot to our understanding about social contagion phenomena, yet it has some handicaps. First of all, we assume that this is an Erdős-Rényi random network. We know that real social networks usually degree heterogeneous. This is one assumption we made. The other assumption we made that everyone has the same threshold. Everyone needs 20% of friends in order to do something. Okay? What if we release a little bit these conditions? If we increase the threshold heterogeneity, where let's say we assume that there is a normal distribution of thresholds with a given standard deviation, what we see that by increasing the standard deviation, the phase space qualitatively remain the same, but the phase allowing for the global emergence for global cascade is expanding, which means that more heterogeneous the threshold distribution is, weaker the conditions that we can induce a global cascade. If we assume a heterogeneous, degree heterogeneous network, the contrary is the true. Larger the degree heterogeneity of the network, the smaller the global cascade regime becomes. More heterogeneous the network, stronger the conditions that you can induce a global cascade. Okay? So this is a very, very charming model. It has been proposed in 2002. It took a long time that actually people had the chance to observe in reality what's going on, to compare to the proposition of Watts. So in the last part of my of the class, we are going to talk about an empirical observation of social spreading phenomena and try to identify mechanisms which were missed by Watts, and we try to extend the Watts model in order to make it even more real than it is. Okay? The problem with the empirical Watts model, first of all, it neglects dominant real-world mechanism. The other is that it is not concerning the evolution of a cascade. If you understood well, what we have here, we have the structural condition for the emergence of a cascade. We have the condition that we need a percolating vulnerable tree. If this tree is there, cascade emerges immediately. We don't care, the Watts model doesn't tell you with what speed it is emerging, it is just saying whether it is emerging or not. The other condition is that there are several different scenarios when you turn to real phenomena. You can actually find scenarios where this is true, so the emergence of the social spreading phenomena, like for example, information diffusion, could be very, very fast. So in this case, the Watts model is telling you, Watts model is a good approximation because it is also predicting you instantaneous spreading of the phenomena. So it means that this model, which is using threshold mechanism and this explosive type or explosive kind of spreading, is good. On the other hand, there are many other problems, like for example, product adoption or innovation spreading. We have seen that it's possible that an innovation is spreading over decades. 50 years, it needed that people started to use electricity in the house. On the other hand, the other type of models, simple diffusion, bus model, are very successful to predict that type of phenomenon, right? On the other hand, what we miss is that social influence plays a role over here as well. So threshold models should be recover slow evolution of cascades, not only rapid evolution of cascades. Okay? So we have this contradiction that we have a good model for rapid cascades and threshold mechanism, which is not covering a large set of phenomena, and we have another model for large set of for these slower phenomena, which does not use thresholds at all. So then what can we do? This is just a further motivation what I have just told. This is the maximum relative growth rate of different online services as a function of time. The Watts case, the Watts model would predict that they are emerging instantaneously, so their maximum relative growth rate is equal to 1. On the other hand, if you really measure them, like for Facebook, Twitter, LinkedIn, Skype, and so on and so forth, you see that actually this bar is quantifying how slow the spreading appeared. You see that they are far from being instantaneous. So Watts model is actually not capturing their overall dynamics in a correct way. So what we need a general model of social spreading, which considers social influence by thresholds, which may integrate other mechanisms, what I'm going to talk about and has been neglected by the Watts model, and can capture all these types, various types of scenario, dynamical scenarios that the social spreading phenomena emerges rapidly, slowly, even slower, or faster. Okay? So what we are going to do now, we take a data. This is actually one of the largest data which were accessible for public research at that time. It is the social network of Skype. Contains 510 million nodes and 4.4 billion links. Nodes are Skype users. Links between them are confirmed Skype contacts. So I don't know whether you use Skype. if you go on Skype, you can assign your friend, and your friend has to confirm that you know each other, and then there is a link between you. So this is exactly the network of this, containing all users and all confirmed relationships. It's pretty big. Fit in the memory, it was a challenge. The adoption spreading, what we are trying to observe is a given service. It's a paid service called buy credit. Why it is a paid service? Because if we would follow a free service, you would maybe just try out a free service without any risk. But once you pay for something, it's a conscious act. So you don't pay for something just by chance, right? Ideally. So what we have a complete set of a social network. Why is it a complete set? Because this product, paid service, was available only for Skype users. So this is actually the network which can maintain the spreading of this product. This product cannot spread out from this network because first you have to become a Skype user in order to buy the product. Okay? What we actually observed, we were looking for the time of first payment. This is what we identified as the act of adoption of the given product. And we were observing it for 89 months, and we observed that 8% of the nodes, of the 510 million nodes, adopted this product, which is not the 100% of the population, but it's still millions of people. Okay? So what do you do first when you have a data like this? You look at its degree distribution. This is a network analysis 1.0. The degree distribution turned out to be the blue distribution. Actually, the gray distribution, the blue distribution is a long bit version of the degree distribution. But it turned out that actually it can be very well fitted with the log normal distribution. So we, after testing different hypotheses, we could claim this is wrong here, it's a log normal distribution, that the degree distribution is a log normal distribution. The second quantity, what you could measure, is actually the adoption threshold. How do you measure the adoption threshold? What you see is that you have a network, you know who is connected to who, and you know when a person adopted the given product. So let's say that I adopted the product today. I can look in my social network, in my Eccentric network, and count the number of my friends who adopted earlier than me. That will give me the numerator of my threshold. The denominator is going to be the total number of my friends. So just by looking at the time when someone adopted the product, how many of them, of their friends, of his friends adopted earlier, gave us actually the threshold. Of course, it's an estimation. We can discuss about this why. But what turned out is that independent of the degree, the threshold, first of all, could be shifted together to a master curve, which could be fitted again by log normal distribution. So the threshold distribution is not a delta function as what was assumed, but actually it's a broad distribution, a log normal distribution. So we have a network which has not an exponential, not a Poissonian degree distribution, but a log normal distribution, and not a delta threshold distribution, but a log normal threshold distribution. Very well. Next, what you can do, you can look actually at the adoption curves. So you can see what fraction of people, how many people are adopting the given product at a given time period. This is the black line over here. And you can decouple this for the rate of innovators, the rate of vulnerables, and the rate of stable nodes. Remember what Watts was claiming, that the condition for the emergence of a global cascade is to have a vulnerable tree. A percolating vulnerable tree, which means that vulnerable tree is supposed to be dominating the process. He also claims, or assumed, that there is only one innovator in the system. So here what we observe, that actually there are not only one innovator in the system, but innovators are coming with a constant rate. They pop up all the time independently, spontaneously adopting the product. Vulnerable nodes, which is the green line here, the red line here, they are not dominating the process, but they grow exactly or very close to the rate of innovators, which means that there could be some strong correlation between vulnerable and innovator adoption, but certainly there are no large vulnerable trees, Otherwise, the vulnerables would drive the adoption. They would have a curve above all of the others. And finally, the blue, the stable nodes, they are the ones which are responsible for the nonlinear growth. They are running the show. So actually, the adoption process is driven by the stable adoptions, not by percolating vulnerable trees. So the picture what we can draw from this it's a big figure. Can be even further sophisticated if you look at the distribution of the adoption network in terms of stable, vulnerable, and innovator nodes. So what it means, at a given time, I take all the nodes who adopted the product, and I consider all the links which are connecting adopter people. It is giving me a network at each time step, right? Then I can look at this cluster size distribution of this adopters network, and I see that as time is increasing, there is a large connected component in the adopter networks, which is emerging and growing and growing. This is already a sign that there is a strong effect of social influence. Why? Because we observe that 8% of the people adopted the product, but somehow they are connected together to a large connected component. The next step, I can actually decouple this adopters network into a vulnerable network. If Watt's claim is true, there must be a large component of the vulnerable network because we assume that there is a percolating vulnerable tree. Instead of that, we observe that the cluster size is exponentially distributed. One step further, we can look at the stable adopters network. And we see that the largest connected component is there. So actually the stable adopter network, which is holding the whole adoption cluster together. So even further to visualize, it's again a very large figure. I'm really sorry for this. Is that we have the network, we have the innovators who adopt the product independently from each other. They are randomly distributed in the network. They locally induce small vulnerable trees, but there is no globally connected percolating vulnerable tree. And these vulnerable trees and innovators actually further induce a large stable cluster which connects the whole adoption cluster together. So it more or less looks like a chocolate chip cake, okay? Where cake is the stable adopter network and the chocolate is the innovators and the small vulnerable trees. This is pretty much the contrary what we expected from the Watts model, because Watts assumed that these red trees, they are the ones which are spread all around the network, and these blue adopters are just on the surface of the vulnerable tree. Very well. I think from here the figures are going to come a little bit faster. How can we model this? It's very simple. We take the original Watts model and we add what we have observed to the model itself. The first thing what we add is we assume that there are spontaneous innovators, not only one, but they are coming with a constant rate as we observed in the original data. Assumption 1. Assumption 2, somehow we have to account for the fact that only 8% of the people adopted the product. How do we do this? We realize that actually it's possible that people just don't give them to adopt the product. Okay, so it's possible that even Apple is trying to sell the iPhone for you, you just don't want to buy it, right? Even so, there are a large fraction of people who are just not interested in a given product. These people, assumingly, are randomly distributed all around the system, and we can control their amount by a given fraction of blob nodes. These nodes are, so to speak, immunized against the product. They will never adopt the given product itself. On the other hand, they are going to dilute our system because they are randomly put all around the network and effectively changing the possible reachable threshold of people in the network. So what we have here, we have 3 different types of nodes in our model. There are the block nodes, the immunized nodes who will never adopt the product, who don't want to buy the product at all. There are the susceptible people who potentially will buy the product, and there are the people who have already bought the product, the adopters. Okay? The model is going as follows. We take a network with a given degree distribution. We assume thresholds for the nodes coming from a given threshold distribution. We initially block an R fraction of nodes. These are the guys who will not buy the product. We initiate, in each time step, we look at each susceptible nodes. Each susceptible node at a given time step can adopt the product in 2 ways, whether spontaneously, with a given probability constant rate as a function of time, or if the threshold has been reached for that given node. Okay? Actually, this system can be described by an approximate master equation formalism introduced by Gleason for any binary types of binary dynamics binary processes. It is based on a representation where it identifies each node as a vector of degree and pretty much threshold. So each node is described by this small vector. And the system can be wrapped in 2 equations. One is giving the probability that a randomly selected node is an adopter, and the other is giving the probability that a randomly selected neighbor of a randomly selected node is an adopter, becoming an adopter at a given time. Actually, you can solve numerically these equations, and what you get is very close what we have observed in the original case. So for our simulations, we took a configuration network model with exactly the same degree distribution as the empirical data. We took thresholds to nodes sampled from exactly the same threshold distribution what we fitted on the empirical data. We have the rate of innovators, the constant rate of innovators fitted from the empirical data. The only 3 parameter what we have is the R fraction of block nodes, but we don't know. Because just by looking at the system, you cannot estimate how many nodes will not adopt the product as the time is going on. So this is what we try to actually determine from our modeling. What we have is that, again, we are looking for the same phase space, average threshold, average degree. And what we observe that if we fix the R fraction of adopters and we vary the time, as time goes by, as we are introducing more and more innovators in the system, the phase which is bounded by the lines, okay, is expanding the phase which is allowing for a global cascade. This is not a miracle because we are putting more and more nodes in the network. A global cascade will apparently emerge if we put enough nodes, innovator nodes in the system. What is interesting, on the other hand, that if we fix at a time, so we are actually stopped at time step 89, which is corresponding to the observation timing of the real data, and we vary R, the fraction of block nodes, actually the phase space is going to shrink. More and more you dilute the system with people who don't give a damn, more difficult that you will receive a global adoption cascade. Moreover, you can also look at the spreading curve as a function of these 2 parameters. If you vary the fraction of innovators, you see that the phenomenon is not changing, only the transition point is going to shift with PM. On the other hand, if you vary R, if R is 0, you have the Watts case, you have a very rapid instantaneous emergence of a cascade, but as you increase R, you can slow down the process. Exactly what we wanted to do. We wanted to have a model which has threshold mechanism and can actually capture many different types of dynamic scenarios, rapid cascades, slow cascades, and so on and so forth. Moreover, we can identify a regime of R, which below it is always instantaneous. And during this regime, there is a critical slowing down. During this regime, actually, there is a period where the system starts to slow down, and there is a period after that, after 0.8, which after there is no possible global emergence of a cascade because it is way more diluted. The whole system, there are too many people who don't give a damn to adopt a given product. Cool. So we have this, I wouldn't say simple, but simplistic model. How can we validate it? The validation is not very difficult actually. What we do is we are making simulations on very large networks as a function of R block nodes. So this is one simulation with 20% of the nodes blocked in the very beginning, 20% of the nodes who will never adopt the product. We are measuring different things. We are measuring the largest connected component of the original network, of the adapter network, that's the yellow, of the stable network, there's the blue, and of the vulnerable network, there's the red. We do the same for the second largest connected component, knowing from pair collision theory that the second largest connected component is associated, the susceptibility should have a maximum at the critical point when the system falls apart. So what we see is that as we are increasing the R fraction of block nodes, of course the network is getting smaller and smaller, as well as the cascade itself. There will be a critical regime which above there is no global cascade anymore, and there is a regime where the cascade evolution is slowing down. So this is simulation. How can we relate this to real data? We can simply take the original adoption network distribution and look at the fraction of the largest connected component in the last time when we observe the network in the data. Since our simulation is corresponding to the same time, we can just match this fractional side to the largest component of our simulated cascade, and we find that actually in case of this product there is 0.73% of nodes who will never adopt the product, which is bad news in a way, because it means that the product can be solved only for the remaining 27%. It's a good news in another way, because our system is in the crossover regime, so there is still possibility for a global cascade. And finally, how can we verify this 73, 74%? We can look for other types of statistics in the network. We can look for the depths of vulnerable trees, and you see that as by varying R, the one we fitted is the one which is falling together with the data, which is the red point. And we can also measure the correlation between the degree of a node and the average size of cluster it induced. And you see by varying R, the one which is fitted from the data is relatively close to what we observe the data. I think this is the point where I have to stop talking. So thank you very much for your attention. I know that towards the end of the class we got a little bit complex. So if you have any question, just ask me. Otherwise, thank you very much for your attention.